By the time we're done today, we're going to have a strategy to graph any polynomial function that we're given. Maybe not any, but most polynomial functions. And we'll find out more strategies for certain areas moving forward in the next few lessons. But today, it's just going to be the basics. And I'm going to start by talking about something called end behavior. And we're going to start talking about end behavior through four graphs, four graph shapes. These shapes, x squared, negative x squared, x cubed, and negative x cubed. Y equals x squared, f of x equals x squared. It's a parabola that opens up. Other x squareds are also parabolas that open up. Negative x squared, that's a vertical flip, so it's an upside down parabola, a parabola that opens down. We spent a lot of time talking about these shapes and minimums and maximums. We even looked at an idea of relative minimum, relative maximum. Here's our y equals x cubed shape, increasing from left to right forever. And if we had a vertical flip, if we flipped it upside down, we'd have negative x cubed. That's decreasing from left to right forever. When we're talking about end behavior, we're talking about what's happening all the way on the left and all the way on the right, all the way on the left and all the way on the right, all the way on the left and all the way on the right, all the way on the left and all the way on the right. We don't care what's happening between all the way on the left and all the way on the right. We don't care about behavior. We only care about ER, all the way on the left and all the way on the right. So there's some different ways we can describe the end behavior, but the easiest is just to say rises and falls. So x squared rises left and rises right. Negative x squared falls left and falls right. Y equals x cubed falls left and rises right. Negative x cubed rises left and falls right. So what's so important about these four shapes specifically? Well, between these four shapes, we have every combination of rising and falling. Rises, rises, falls, 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 rises, rises, falls. That was a nice little ditty. So we have every combination of rising and falling. These are actually four helpful graphs because this one acts the same as any positive, even exponent. Positive base even exponent. This one, any negative x to an even exponent. So negative with even exponent acts the same as negative x squared. 3 cubed. The cubes act like all the odd numbers. So all positive x to an odd power act like positive x cubed. All negative x to an odd power act like negative x cubed. So all positive x to even powers act like positive x squared, rises to the left, rises to the right. All negative x to even powers act like negative x squared and fall to the left and fall to the right. All positive x to odd powers act like positive x cubed, fall to the left and rise to the right. And all negative x to odd powers act like negative x cubed, they rise to the left and fall to the right. So if you remember the orientations of your x squared and your x cubed, and you know you can flip them upside down to get negative, then it's just a matter of remembering our old parent graphs and knowing what an even number or an odd number is, and we've got this. So what exactly do we look at? I keep saying that we just look and then we compare and then we're done. Well, before I talk about what we have to look at, we should remind ourselves of some terminology that relates to polynomials and therefore to polynomial functions. The terms being things separated by plus and minus, so this has 3 terms. The term that has the highest power of x, in this case x squared, that's called the leading term. Leading doesn't necessarily mean in front. If it's written in decreasing power of x, yes, it will be in front. But the leading term is the term with the highest power of x. That highest power is called the degree. So here we would say this has a degree of 2. The leading term, the term with the highest power, the term that determines the degree of the function, is what we look at. In this case, we're looking at 4x squared. That is a positive x to an even. So just like x squared, it's going to rise to the left and rise to the right. So if we had to write out the end behavior, that's one way of doing it. Or we can say rises to left, rises to right. The fancy math way, fancy math way, is to say as we go to the left, in other words, as x approaches negative infinity, as x goes to the left, f of x, or in this case, h of x, but let's make that an f just so I can use f of x here. It rises, it goes up, so the function goes up. As x approaches negative infinity, f of x approaches positive infinity. As we go to the left on the x, the function goes up, approaches positive infinity. That takes care of our left. For our right, we would say as x approaches positive infinity, as x goes to the right, f of x rises, f of x goes up. F of x would go to positive infinity. So that's 3 different ways of saying the same thing. Obviously, we like this one. That's just 2 little arrows. It's the easiest to write. But you have to be able to understand that all 3 of these mean the same thing. You need to be able to recognize how to read this. As x goes to negative infinity, as we go to the left on x, f of x goes to positive, we go up. Left rises. As we go to the right, as x approaches positive infinity, f of x approaches positive infinity. Right, up. Let's look at more end behavior. New function, new f of x. Let's say f of x equals negative 4x to the 5th plus 6x to the 4th plus 2x. What is the end behavior? Well, we have to find the leading term. That's the highest power of x. That's x to the 5th. This is negative x to an odd power, which is going to act like negative x cubed, which is this one. So it rises to the left, falls to the right. That's it. Rises left, falls right. Or left as x approaches negative infinity, f of x left is rises. F of x goes to positive infinity. As x goes to the right, as x approaches positive infinity, we fall. F of x approaches negative infinity. 3 ways of putting the same answer. In the words of, is it copyright infringement if I say it? Another one. F of x equals negative 0.3 x to the 4th minus 5x squared minus 3x plus 4. You're going, oh, decimal's scary. Don't forget what we're doing. We're finding the end behavior. That's it. Highest power of x, x to the 4th. So this is the leading term. This is a negative x to an even power. That means it's like negative x squared, which looks like this. So it falls to the left and falls to the right. Falls left, falls right. To the left, as x approaches negative infinity, f of x, it falls, it approaches negative infinity. As we move to the right, as x approaches positive infinity, falls to the right. F of x approaches negative infinity, goes down, whether we're going to the left or the right. I think it's time to wash my eraser again. This one's a little challenging looking. G of x equals 1/4 x times 2x minus 3 cubed times x plus 4 squared. Now, when it's written like this as factors, not multiplied out, expanded, parentheses gone, seeing it in its number of terms, right now, the leading term is hidden from us. But we don't need to figure everything out to get the leading term. We just need the first term of each of these. Yes, we could do 2x minus 3 times 2x minus 3, foil those, get an answer, and multiply it by 2x minus 3 again to get that 2x minus 3 cubed. Then multiply that by x plus 4 times x plus 4. Multiply all our answers together, multiply it by 1/4 x, and then see what the leading term is. But that is a lot of work for no reason at all. We just need the first terms, and we can get those. The 1/4 x. And then here, if we cube the first term, that'll give us the first term, the leading term. So that would be 2x, and I'm going to get rid of this equal sign. This is implying that I'm finding the equal. I am just looking for the LT, the leading term. 2x gets cubed. Here, the x gets squared. This is not how we would figure out what this is. We're just looking for the leading term. This is going to be a 1/4 x times an 8x cubed times an x squared. 1/4 times 8, it's 8/4, that's 2x to the add the exponents. 1 plus 3 is 4 plus 2 is 6. So our leading term is going to end up being a positive 2x to the 6th. So we just multiply the leading terms from each factor. We get those by just figuring out what the first thing to whatever power would be. We didn't have to find the rest of it. Once we have the leading term, this is a positive x to an even power, like positive x squared, which looks like that. So it rises left and it rises right. Let's do one more of these. Hopefully this hasn't been so bad so far today. Just keep up with what we're doing, putting it in the lecture. It is important. You should be able to do it without any help before the test. To be truly prepared for the test, if you were to pick any random problem from any video that's covered on the test, and you start a problem and you pause it, if you can't get it right without looking in your notes, you're not ready for the test. It's as simple as that. Being able to work in the homework while you're looking in your notes, that's one thing. That's not being ready. Being ready is saying, hey, can I do this without any help? Yes or no? G of x, 6/7 times x minus 9 to the 4th times x plus 4 squared times 3x minus 5. This is going to be a not equal to, we just want the leading term. The leading term is going to be 6/7 times x to the 4th times x squared times 3x. That's going to be 18/7 x to the 4th x squared x. That x is to the 1st. 18/7 6 x to the 7th. 4 plus 2 plus 1. That is a positive x to an odd. So it's like positive x cubed, which looks like this. So this graph falls left, rises right. down to the left, up to the right. Okay, now we can find end behavior. This is important. This is a piece that we're going to be using to do our graphs, along with x-intercept, y-intercept, other things that we know how to do. So now that we've got end behavior, let's start talking about zeros. And we're going to talk a little bit about zeros today, enough to get some graphs going. But the next lecture is going to be all about what we can do to find zeros, lots of different ways and different situations. So first of all, what do I mean by a zero? Well, zeros are going to be x-intercepts. Why are they called zeros? They're places where the function value, where the y, where the output is equal to 0. Y-intercepts are where f of x or y equals 0. AKA y equals 0, just to drive that point home. Right now, if you're going, where is this coming from? We've been working with this all semester. Intercepts were a tool in our toolbox. We learned how to do it. The first part of this course has been putting tools in our toolbox. We're now going to start combining it with the math from the previous classes to just do more different things all the time. But these new different things we're learning, they're also going to be tools that we could be using for future problems. Math in real life is not nice, neat numbers like this, but it's through working with these basic, not to make them sound easier than they are by calling them basic, but I just mean basic as in not weird decimal numbers, things that occur in nature. The math that gets used in the real world uses real data, but uses the same methods that we would use on nice numbers that are easily manipulated. Okay. So how can we find zeros? Well, let's start with f of x equals x cubed plus x squared minus 9x minus 9. Now, we haven't really needed it much up until now, but from this point on, if you can't factor, you are in trouble. If you can't factor, I urge you to seek out my factoring videos. Ask me for them if you need to. It's something that is required coming into the course. So when we have 4 terms, our strategy first, always see if there is something in common to all 4 terms. And we don't have anything that can come out of all 4. So we have to do factoring by grouping. Group the first two terms. From the first two terms, we can take out an x squared. We're left with x plus 1. Terms 3 and 4, since this is a minus, we have to factor out at least a negative. We can factor out a negative 9. We're left with negative 9 times x is negative 9x. Negative 9 times positive 1 is negative 9. That means we can factor out the common factor of x plus 1. We are left with the leftover x squared minus 9, which can be factored further. X squared minus 9 is x plus 3 times x minus 3. So why did I factor? Well, it's because to find the zeros, to find the x-intercepts, we want to set the entire function equal to 0. Not plug 0 in, set the whole thing equal to 0. And when we have 0 on one side, what we would really like is everything completely factored on the other side, because then we can use the zero factor property. What is the zero factor property? Well, I'm glad you asked, but I'm sure you remember, and I'm sure once I say it, you'll go, oh yeah, I remember that thing. When we have a bunch of things multiplied together equaling 0, we just set each equal to 0 and solve. So 0 equals x plus 1 means x equals negative 1. Subtract 1 from both sides. 0 equals x minus 3. Subtract 3 from both sides. X is negative 3. 0 equals x minus 3. We'd add 3 to both sides. X equals 3. So 1, 2, 3, these 3 zeros for this function are what we get when we solve for x when the whole function is equal to 0. X equals negative 1, x equals negative 3, and x equals positive 3. Those are the zeros of this function. Let's do another one like this. Let's find the zeros. I'll make it another factoring by grouping problem as well. F of x equals 4x cubed minus 4x squared minus 25x plus 25. We want to set the whole thing equal to 0, so we'll begin factoring this side so we can solve. Nothing can be factored out of all 4 terms, so we have to factor by grouping. If we group the first 2, we can take out a positive 4x squared. We're left with 4x squared times x is 4x cubed. 4x squared times negative 1 is negative 4x squared. And I hate to be a downer, but if you're not willing to learn this now, if you didn't know it coming into the course, that means that this is in fact too high of a course for you and you need work in the lower course in the front half of the book. You're going to start coming across a lot of math from the front half of the book now. That's what's going to make this class more difficult. If you're good with the front half of the book, if you're good with the previous class, the previous course, then it's just going to be little additions every class, and this will be very manageable. The big struggles you're going to have now are not struggles with this course. They're struggles with the last one. We have a minus here. That means we have to factor out at least a negative. We can actually factor out a minus 25. Negative 25 times x is negative 25x. Negative 25 times negative 1 is positive 25. We now have this common factor of x minus 1 that we can factor out. We're left with 4x squared minus 25. This is a difference of squares. This can be factored further. The two things being squared are 2x and 5, 2x and 5, and for a difference of squares, that's 1 plus and 1 minus. Don't forget our x minus 1. And that is the completely factored form. Now we can use the zero factor property, the zero product property, set each of these equal to 0 and solve. X minus 1 equals 0 means x equals 1. 2x plus 5 equals 0 means 2x equals negative 5, means x equals negative 5 halves. 2x minus 5 equals 0 means 2x equals positive 5, means x equals positive 5 halves. So those are our 3 zeros of this function. We just found x-intercepts. These are points that we can put on the graph. You know what happens when we put points on the graph? And we know what our end behavior is. And we can find the y-intercept too. The y-intercept is plugging 0 in for x. That makes these first 3 terms go away. F of 0 would be 25. That's a y-intercept. These are points that we can draw through. We know end behavior, so we know where they're going and where they're coming from. We're almost there. We can almost draw graphs. But let's find more zeros first. We need more practice. F of x equals negative x cubed plus 8x squared minus 16x. First step, set the whole thing equal to 0. Factor. We can take out, well, when the leading term is negative, we can always take out a negative. And we can take out an x. So we're factoring out negative x. 3 pieces in the original, 3 pieces in the leftover. Because factoring out a common factor, that is thinking about the distributive property in reverse, thinking about the steps. Negative x times positive x squared is negative x cubed. Negative x times negative 8x is positive 8x squared, negative times negative is positive. Negative x times positive 16. Negative times positive is negative 16x. This you either have to recognize as a perfect square trinomial, or you have to look for the two numbers that multiply to give us 16, add to give us negative 8. That's negative 4 and negative 4. So x minus 4, x minus 4. And when we have a repeated factor, we write it as a square. So negative x equals 0, or x minus 4 squared equals 0. So negative x equals 0 means x equals 0. Square root both sides. X minus 4 equals plus or minus the square root of 0. That's just 0. Add 4 to both sides. X equals 4. So x equals 0 and x equals 4 are the zeros. They are the x-intercepts. X-intercept, that's a point. Ooh. That is a point where y is 0. So 0, 0, and 4, 0. These are points that we can use to graph this. We wouldn't just want to put a line through those points because it's not a line. How do we figure out the ups, the downs, where they're going, where they're coming from? End behavior. All these things we're learning about. You'll see it all come together very soon here. We're going to find out how to find multiplicity of zeros. And we're going to find out what it means to have an even multiplicity. And we're going to find out what it means to have an odd multiplicity. When we get to the end of a factoring problem and we have to do the zero product property, if it's just something like this, we go x minus 3 equals 0. That means x equals 3. We have x plus 2 equals 0. That means x equals negative 2. The things we solved came from linear factors. The x minus 3 wasn't raised to any fancy power like a square or a cube or a 4. It was just to the first power. The x plus 2 wasn't to any fancy power like a square or a cube or a 4. It was just to the first power. So these zeros would have multiplicity of 1. Let me drive this point home. We just did an example. where we ended up with negative x times x minus 4 squared. That was equal to 0. So we did negative x equals 0. We did x minus 4 squared equals 0. We got an answer of x equals 0. We got an answer of x equals positive 4. These were the two zeros. They came from these two factors. Since this x wasn't any fancy power, it was just x to the first, this 0 has a multiplicity of 1. Since this 0 came from, it's got a fancy 2, that means this 0 has a multiplicity of 2. An even multiplicity versus an odd multiplicity. An even multiplicity bounces off the x-axis. An odd multiplicity crosses the x-axis. Even multiplicities bounce, odd multiplicities cross. So just like we have end behavior, where we can figure out what's happening on the left and right, maybe just, yay, okay. We also now know what's happening at the zeros based on the multiplicity. The zeros just tell us that they're on the x-axis. The multiplicity tells us if we bounce off or if we cross at the x-axis, which is useful when you're trying to draw a freaking graph. So if we had m of x equals 1/10 x minus 4 squared times 2x plus 5 cubed, the zeros we would get from this, we wouldn't get anything from the 1/10. We'd get x equals 4 with a multiplicity of 2. And we'd get 2x plus 5 equals 0, so 2x equals negative 5, x equals negative 5 halves, and it has a multiplicity of 3. Even multiplicity bounces, odd multiplicity crosses. Okay, before we finish up with doing a graph, I want to talk about something called the intermediate value theorem. And I want to talk about how it's really common sense. The intermediate value theorem says for a less than b, if f of a and f of b have opposite signs, then f of x, or f, has at least one zero on the interval from A to B. That's wordy. That is wordy. For A less than B, if f of A and f of B have opposite signs, then f of x has at least 1, 0 on the interval from A to B. So once I break this down and explain what it's saying, like I said, it's going to be common sense. A and B are x values. We know that because we're plugging them into the function. We know that because they are endpoints of an interval. A is less than B. That's just saying A is the smaller number and B is the larger number, as it would have to be if it would be written in an interval like this. F of A and F of B, these would be the y values for A and B. If we plug A in for x, we have f of A. If we plug B in for x, we have f of B. If we think of a graph, if let's say that's A and that's B. If f of A and f of B have opposite signs, that means they're on opposite sides of the x-axis. That means to get from A to B, we have to cross the x-axis. That means there's at least 1, 0 in between A and B. That's all this theorem's saying. This theorem's saying if we have to cross the x-axis, then we have to cross the x-axis. Let's do a problem with the intermediate value theorem. Show that f of x equals x to the fourth plus 6x cubed minus 26x plus 15 has a 0 on the interval from 1 to 2. So there's A and there's B, 1 and 2. Let's find f of 1. That is 1 to the fourth plus 6 times 1 cubed minus 26 times 1 plus 15. 1 to the fourth is 1 plus 6 times 1 cubed. 1 cubed is 1 minus 26 times 1 is 26 plus 15. 1 plus 6 times 1 is 6 minus 26 plus 15. 1 plus 6 is 7 minus 26 plus 15. 7 minus 26 is negative 19. Negative 19 plus 15 is -4. So f of 1 is -4. Now let's find f of 2. F of 2 would be 2 to the 4th plus 6 times 2 cubed minus 26 times 2 plus 15. 2 to the 4th is 16 plus 6 times 2 cubed. 2 cubed is 8 minus 26 times 2 is 52 plus 15. This is 16 plus 6 times 8 is 48 minus 52 plus 15. $16 plus 48. 14 plus 50, 64. Minus 52 plus 15. 64 minus 52 is 12 plus 15. 12 plus 15 is 27. So f of 2 is positive 27. So far, all we've done is plug in 1, and we've plugged in 2. F of 1 is -4. F of 2, way up there, is 27. That means to get from 1 to 2, we have to cross the x-axis. So we have shown that it has a 0 on this interval. Why? Because f of 1 and f of 2 have opposite signs. -4 versus positive 27. That's how we use the intermediate value theorem. So I'm going to show off here the end of this lecture. By throwing a graph together, we're going to do much more practice with this in the future, drawing these graphs. Let's take a look at what we can do with f of x equals x cubed minus 9x. So first off, let's find the end behavior. This is positive x to an odd power. It's literally x cubed. That means it's going to fall to the left and it's going to rise to the right. If we set it equal to 0 to find the zeros, factor and solve, we can factor out an x. We're left with x squared minus 9. That can continue to factor x plus 3 times x minus 3. These are 3 zeros, x equals 0, x equals -3, and x equals positive 3. They all have multiplicities of 1. So they are all odd multiplicities. They are all cross points. These are x-intercepts. How would we find the y-intercept? Plug 0 in. F of 0 would be 0 cubed minus 9 times 0. That's 0 minus 0. F of 0 is 0. So 0, 0 is the y-intercept, but it's also an x-intercept. These cross points, 0, 0, negative 3, 0, and 3, 0. So let's plot the 4 points we have. Zero, 0, 0, 0 again, negative 3, 0, positive 3, 0. The end behavior, to the left, it has to fall. To the right, it has to rise. And all 3 of these have to be cross points. So if it's falling all the way off to the left, that means it's got to come up through that one. And since it has to cross here, it's going to have to come back down through, and then it's going to have to cross here. So it's going to come back up, which tracks with rising off to the right. So somewhere in here, it's going to have to fall back down. Somewhere here, it's going to have to go back up, which means we're going to have a relative maximum over here. We're going to have a relative minimum here. To make this, notice I didn't put any tick marks on the y-axis because I don't actually know how far up, how far down it's going to go. How can we figure that out? We can plug values in between. So the more values we plug in for x between the x-intercepts, the more accurate we can get as to our graph. And we know how to plug points in. We did that at the beginning of the course a lot. So the more accurate of a graph we need, the more points we have to plug in for x in between, find our y values, plot more points, and draw through.